Let's take a look at the group 2 alkaline earth metal. In terms of atomic radius, it will increase down the group, given the fact that the increase in shielding effect is more significant than the increase in its nuclear charge. Since the increase in shielding effect is more significant than the increase in nuclear charge, given the fact that the outermost electrons will increasingly be further away from the nucleus, hence the increase in electrostatic attraction force by the nucleus on the outermost electron is mitigated. Hence, the ENC decreases down the group and atomic radius increases. In terms of ionization energy, same reason as stated earlier, but one more factor to add, which is to state that the increase in shielding effect coupled with a larger atomic radius outweighs the increase in nuclear charge. So we expect the ENC to decrease down the group. So the first IE of the alkaline earth metal decreases down the group. And the reasons for decreased electronegativity and ionization energy are the same. Melting point wise, in terms of metallic bonding, metallic bond will be weaker when you go down the group, primarily because that your atomic size will increase, which means the charge density of your cation will decrease as your cationic size becomes bigger as you go down the group. So the melting point is expected to decrease down the group. In terms of reducing power, we noted that all the metals are the right-hand species in the standard electropotential value. And if you look at the standard potential values, the values become more negative as you go down the group. Therefore, indicating that the reactions can move from right to left, and hence the reducing power of your alkaline earth metal increases down the group. So which means when you go down the group, the metals become stronger reducing agent. So reaction with oxygen, all of the group 2 metals can react with oxygen to form your oxide as governed by this equation here. Certainly, barium is a lot more reactive than your beryllium, which is the reason why you find that the beryllium hardly reacts with the steam. Mindful that the beryllium oxide, beryllium like aluminium, are very similar to each other. So beryllium easily forms an impermeable inert layer, BEO, that helps to prevent beryllium from reacting with water molecules. As far as magnesium is concerned, magnesium reacts very slowly in the presence of water, all right? But it reacts vigorously in the presence of steam to produce your magnesium oxide and actually your hydrogen gas. So that reactions and experimental setup was taught actually at the whole level. Calcium onwards, all of them are able to react with your water molecules to form hydroxide and your hydrogen gas. However, we need to note that for the case of calcium hydroxide, depending on the amount of water present, calcium hydroxide may actually end up as a precipitate because calcium hydroxide's solubility in water is pretty poor relative to your strontium hydroxide and your beryllium hydroxide. And by the way, calcium hydroxide is actually used to test for carbon dioxide. So in the presence of, if you put some CO2 inside, you will actually get your calcium carbonate being precipitated. Next, reactions of oxides with water. BEO, by the way, is an exception because it shares similar properties with your aluminium, as explained in the topic on diagonal relationship. And therefore, BEO is in fact amphoteric, so it does not dissolve in water. We can also explain that by actually talking about the extremely high lattice energy of BEO, given that the Be2 plus has a high charge and the Be2 plus has a extremely small ionic radius. When it comes to magnesium oxide reacting with water, it's also sparingly soluble. So you will learn later that because it dissolves very poorly, so the solution that you get is just mildly alkaline. Finally, all the oxides are able to react with water to give hydroxide, and in the same vein, we'll find that calcium hydroxides is the only one that might actually cause precipitations. All right, all the reactions that we described down here, all these are all exothermic. Okay, now we look at the reactions of group 2 peroxides with water, and before that, we need to note that all of these compounds are unable to form a stable peroxide. Reason for that is that this is the structure of peroxide. So it has a pretty large electron cloud. So if your charge density, which is for group 2 is this, if your charge density is too high, then what it does is that you will polarize it, so much so that they will break. Okay, so that you will cause the O to O bond to break in the peroxide molecule, forming your oxide, which is actually more stable. So the point to make is that all these group 2 cation has high charge density, so therefore polarizes the large electron cloud of your peroxide, rendering the peroxide unstable, which is the reason why you're not able to produce a peroxide for all of them. So the first peroxide that is deemed to be stable is your beryllium peroxide in your group 2. Of course, going down the group and beyond barium, you do have peroxide which are pretty stable as well. So barium peroxide can react with water, in this case, to form your barium hydroxide and as well as hydrogen peroxide. So the reaction is actually non-redox actually, because if you think about it, the oxidation state of all the oxygen, like which is actually your -1, and your barium, which is +2, all of them, the oxidation state does not change. All right, and barium peroxide, when dissolved in acid, all right, will be able to produce again hydrogen peroxide and actually the salt, barium sulfate in this case. And if you remember back in O-level, barium sulfate is in fact insoluble. So therefore, it's actually going to form a white precipitate. Next, thermal decompositions of carbonates, nitrates, and hydroxide. So all of them are able to undertake thermal decomposition, all right, based on the reaction that is indicated here. So probably the one that's a bit new is actually at A level will be the thermal decompositions of your nitrate that will produce NO2 and also oxygen as well. NO2, by the way, is actually brown in coloration. So there's observations that you could make. In terms of looking at the thermal stability, again, in this quite similar to the explanation we gave earlier for peroxide, thermal stability increases. All right, the reason is because you have a very large anion, its charge density is extremely high. You will start to polarize it, and this will actually cause the larger anion to actually cleave its covalent bond, forming either gases or other anions. So bear in mind, thermal stability increases down the group, which also means that thermal decomposition temperature decreases down the group. So you need a lower temperature to actually decompose, for example, barium nitrate relative to magnesium nitrate, which may need a higher temperature. Okay, we'll now take a look at some of the atypical behavior of beryllium, because beryllium, like we mentioned, share a diagonal relationship with your aluminum. It has a smaller ionic radius, so it has a high polarizing ability, very much like your Al3+, and its ionization energy is also significantly higher. So bear in mind that the beryllium, like your aluminum, exhibits amphoteric properties, so it's chemically able to actually react with both acid and alkaline. Both these equations you need to know. The other contrarian behavior that we see is that beryllium chloride is simple covalent. It's unlike your magnesium chloride and the rest of the other group 2 chlorides, they are all ionic. On the other hand, Li lithium and magnesium will share a similar diagonal relationship. So, which is the reason why in this case, lithium carbonate will tend to behave more like a group 2 carbonate. Otherwise, for group 1 carbonate, we all know they are all soluble in water, but not the case of your lithium carbonate. Next, lithium carbonate is able to thermally decompose to form carbon dioxide, like group 2 carbonates. You will learn in the O level that group 1 carbonate actually does not undertake thermal decomposition. Lithium nitrate will now decompose to form nitrogen dioxide and oxygen, again like group 2 nitrate. However, group 1 nitrate, you will learn at O level that only decompose to form oxygen, and you will produce a nitrite. Lithium peroxide and magnesium peroxide are deemed to be unstable due to the high charge density. This is again in contrary what we expect, because group 1 peroxide generally are stable, all right, because group 1 has only got a charge of +1. Finally, Li plus and Mg2 plus could also form complex ions, and in this case, lithium being actually in the period 2 element could only have a coordination number of 4, because it can take up to a maximum of only 8 electrons, as it does not have any D subshell. Unlike the case of magnesium, the coordination number can go up to 6, since magnesium has got a 3D subshell. Now let's take a look at the summary. When you go down the group, the relative ease of electron increases, the relative ease of losing electron increases as the electrons is further away. Therefore, because of that, standard electropotential values becomes more negative, as now metal can easily oxidizes, and therefore, if you go down the groups, the metals become stronger reducing agent. And given the fact that if you go down the group, the standard electropotential becomes more negative, it means that the metal are actually more reactive. So the reaction of metal with water increases down the group, and reaction with steam also increases down the group. If you look at the metal atoms, the size gets larger as it has a larger electron cloud. So the melting point will decrease down the group, given the fact that the metallic bond has in fact been weak. In fact, the metallic bond is weaker, given the fact that in the giant metal lattice structure, the size of the cation is bigger, so the charge density of the cation is weaker, and so the electrostatic attraction with the delocalized electron is weaker, and hence the metallic bond is weaker. So the melting point decreases down the group, so the enthalpy of atomization down the group ought to be less positive. All right. The size of the cation would actually increase in this similarly, following the same trend as that of the size of the metal. So the charge density of the cation, or the polarizing ability of the cation, decreases down the group, which help to explain why the enthalpy of hydration becomes less negative. But since enthalpy of hydration is directly proportional to charge density. Finally, electronegativity also decreases down the group. And if it decreases down the group, the difference in electronegativity between your oxygen and, say, for example, your beryllium will be this. So there's a difference. And in the case of magnesium, it will be further down because magnesium is less electronegative. So the difference in electronegativity will increase when you go down the group for a group 2 oxide. And therefore, because of that, we expect the ionic character to increase, and conversely, the covalent character has to decrease. And since electronegativity is defined as the ability to gain electron, electropositivity is the ability to lose electron. So if you go down the group, the electropositivity ought to increase, easier, lower first IE, easier to lose electron. And therefore, because of that, the summation of the first and second IE becomes less positive. And finally, to wrap up, if you look at the pH of the chlorides down the group, you will notice that the BeCl2 has a pH of 3 to 4. That portion you learn it in your period 3 elements. And magnesium chloride is pH is actually 6.5 when dissolved in water. That you also learn in period 3 chloride specifically. Beyond magnesium chloride, they will tend towards the neutrality pH of 7. So therefore, if you look at the pH of chlorides, of down the group, the pH does increase towards 7. Let's finally take a look at the stability of compounds. So down the group, stability of compound increases, so relative ease of decomposition decreases, so the decomposition temperature increases down the group as the compound becomes more stable. Charge density of cation and polarizing ability decreases down the group, we mentioned earlier. So the peroxide, nitrates, hydroxide, and carbonate become more stable, so stability increases down the group, and instability decreases down the group. And if you look at the size of the cation, they become larger down the group. The lattice energy of ionic compound is less negative because the R+ is larger, so the inter-ionic radius is larger. And the enthalpy of hydration is less negative because the charge density is lower in this case. Reactivity of the oxide increases down the group. Solubility of oxide in water increases down the group. And reactivity in water becomes more exothermic down the group as well. pH of group 2 chlorides we mentioned earlier. So the pH starts from 3 to 4, 6.5, and then goes towards 7. So the acidity of the aqueous solution actually decreases down the group. The solubility of hydroxide increases down the group. So beryllium hydroxide is not soluble. Your magnesium hydroxide is not soluble as well. And so your calcium hydroxide is sparingly soluble. And beyond barium hydroxide, they are all soluble. So solubility of hydroxide increases down the group, while the solubility of sulfate decreases down the group. Later we'll see the reason why. Okay. So with this, let's take a look at the reason why. So first, let's take a look at the solubility for actually group 2 sulfate. So if you look at group 2 sulfate, this is actually the energy cycle. From the energy cycle, we know the enthalpy of solution is equal to enthalpy of hydration, which is this, plus negative of the lattice energy, which is this one. So down the group 2 sulfate, we all know that the R+ will have increased. This value and this value will increase. Therefore, what happens is that in terms of both the magnitude, they are both dropping. So how then are we able to conclude that who drops more? We're able to conclude that because sulfate has a very large anionic size. And because the anionic size of sulfate is very large, which is this, so the R- is very large. So this is the expression of the lattice energy. So we can see that if your ionic radius of your sulfate is very large, it means that when R+ increases, the overall denominator stays relatively unchanged. Since we know the ionic radius of sulfate is significantly larger than the ionic radius of your group 2 cation. So therefore, because of this, we're able to conclude to say the lattice energy stays relatively the same when you go down the group, since the denominator is dominated by the ionic radius of your sulfate. However, in the case of hydration energy, the R plus will increase, which means that the magnitude of your hydration energy will decrease. So this hydration energy will drop, and it means that this value will become less exothermic. If the enthalpy of hydration becomes less exothermic, the enthalpy of solution also becomes less exothermic, and consequently, the solubility decreases. So that helps us to explain for the case of group 2 sulfate. On the contrary, when you look at the group 2 hydroxide does not have the same issue as your sulfate, because the ionic radius of OH minus is comparable to that of M2 plus, which is the reason why if you were to go down the group, you will end up that the decrease in the enthalpy of hydration is less significant than the decrease in the lattice energy. And therefore, because of that, you will end up with enthalpy of solution being more exothermic, and so the solubility increases. Finally, what we have down here are actually all the reactions that you will need to know for involving group 2. Specifically, the one that is marked in red, because those involve your peroxides, which is typically asked at A level, and the other one involves metallic nitride, that's labeled. And these are all the reactions that you see in terms of thermal decomposition.